Okay, I thought I'd show you how to run an ANOVA so that you can actually do one of these if you prefer, if you'd like to. I know it's not one of our homework assignments, but it's still important to learn how to run the analyses, and this will also help you learn how to interpret them as well. So here we are in our data set for the second assignment, right? And in this case, we're going to go ahead and run a one-way ANOVA and then a two-way ANOVA. Okay, so let's start with the one-way ANOVA. So we know with an ANOVA we need at least 3 levels to our independent variable. So our independent variable is the variable that's being manipulated generally by the researcher to test its effects on the dependent variable. So in this case we're going to use, we don't have an intervention, but I took one of the variables that I created for this purpose. I called it quad BMI. So what I did was I took the BMI variable and I divided it into quartiles, right? So I took the lower 25%, the second highest 25%, the second lowest 25%, the second highest 25%, and then the highest 25%. So we ended up having 4 groups here, and you can see based on the coding, 0 is low BMI, 1 is moderate, 2 is higher, and 3 is highest. Okay, so we're going to run that, and we're going to test its effects on, well, let's say on, well, BMI on perceived physical appearance. That should be interesting, right? So I don't know what you predict. You may predict that people with higher BMIs have lower perceived physical appearance, or they may have higher perceived physical appearance. And after that, we'll run a second analysis where we'll add the sex variable into the picture. I call this variable male, where 1 is equal to male and 0 is equal to female. So we'll start with the one-way ANOVA first. So go to Analyze, and we go to Compare Means. So this is a one-way ANOVA. Excuse me. All right, so what's our dependent variable? It has to be an interval ratio variable, also known as continuous variable. We say we'd use perceived physical appearance. Let's throw that in there. Then we need to know what our factor is, and in this case our factor is going to be the 4-level BMI variable. We also call these analyses factorial designs. We call these independent variables, or group. I can also use the term grouping variable. We call them factors. Okay, so now we talked already about doing post hoc analyses or doing contrasts. Contrasts are when we compare when we just compare different groups we planned it in advance, or post hoc is where we just compare all the groups after the fact. So let's go ahead and run a post hoc comparison. And we'll just do the Bonferroni, which I mentioned is the simplest of the ones to use. Okay, but we could also try another one, so least significant difference and 2p's. These are really popular ones that are used a lot. Okay, and then we'll move forward from there. And these are assuming equal variances. There's also ones that do not assume equal variance. We may have to change this after we look at our data. So let's continue here. And is there anything else I wanted me to look at the options? Anything interesting here? Nothing here right now. We're not going to do contrast because, again, contrast would be planned in advance. We could do that to save us a little power, but let's just hit OK now. Okay, so let's see. Did I ask for equality of variance test? I don't know if I did. I don't think I did. So let me go. I'm going to go back and ask for that test because I want to make sure you know how to do this. I always end up clearing everything because I don't like to have too much output here. So let's go back to the Analyze. Compare Means, one-way ANOVA. I thought that was an option. Let's see. Means plot, fixed homogeneity of variances. There it is. That's what I wanted to do. Yes. Now hit OK. All right. So this is going to do Levine's test for homogeneity of variance, and we didn't pass the test. You should know why. If you don't know why, think about it a little bit here, right? So remember, our goal is to fail to reject the null hypothesis. And at an alpha of 0.05, we reject it because our p-value is smaller than alpha. It's 0.04, so it's not good. So we can't use some of the post hoc tests that I proposed. So these data here are really meaningless to us. Let's go back and run it again then. So I'm going to edit, select all, and hit delete. Let's go ahead and run it again. So compare means, one-way ANOVA, and post hoc contrast. So we're not going to use any of these here. This, it says here equal variances assume. We can't assume equal variances. So I think we should be okay with these. Right? Yes, let's try these. Let's see what comes up. Actually, I've decided let's use the game's howl test instead of these other ones. Because we do have unequal variances, but we have roughly equal sample sizes because I divided everything into quartiles, so we're generally going to have equal sample sizes. If we didn't, we'd use some of these other options. In fact, if you go to our lecture, I gave you these. This is actually colored differently, but I gave you these different options to do. So if we have unequal sample sizes or we have unequal variances, we'd use this one here because our sample sizes are roughly equal. So let's go ahead and do that and hit continue and OK. Okay, so now we get a better output. Okay, so everything remains the same here. Overall, we find that there is a difference between groups because here are the results, just like we did when we saw the lecture. You have your between, your within groups, sums of squares. You have your degrees of freedom for each group, right? So within plus between will equal total degrees of freedom, just like within sum of squares plus between sum of squares will equal the total sum of squares. We get our mean square for the between and our mean square for the within. Remember, between and within, this terminology is the same terminology as model and residual, right? So you can use any of these terms, but you should be familiar with all of them. And the f-test is the ratio between the between groups mean squares and the within group mean squares. And you can see that this probability value is 0.002, which is much less than 0.05. So it's pretty strongly significant here. And this just tells us, and again, we know the ANOVA is an omnibus test, so it just tells us that there's a difference among the different groups of BMI, right? Now, we don't know what the differences are until we actually take a look at the post hoc analyses here. So the way you read a table like this is, you'll see on the left column here we have each of the 4 different groups, right? Low, moderate, higher, and highest. And then we also have its comparison. So this would be low versus moderate, low versus higher, low versus highest. Here you have moderate versus low, moderate versus higher, moderate versus highest, and so on. And you get the differences in the means between the groups, right? And then you get the standard error of that difference and the significance level. So you're going to look at the significance level. As we can see here, there's only one significant finding, and it's the comparison of the moderate to the highest BMI. So which one is bigger? So it's moderate minus highest. So a higher BMI tends to have higher perceived physical appearance here, right? Yep. So it's I versus J, yeah. So I don't know if that's counterintuitive, whatever it is. It shows that there's a difference. Okay? So that's for the post hoc test. And again, remember that the null hypothesis is that the difference is equal to 0, so the alternative hypothesis is that it's not equal to 0. So if we look at the confidence interval, this confidence interval should not include 0, right? So where's the significance? Right here it is. Yep, 0.2 to 0.97 does not cross through 0, so we know that's significant. Okay, so now let's move on to the Nway ANOVA. So when we're doing the Nway ANOVA, we have more than one grouping variable or more than one independent variable. So in this case, let's go back to our data, and here we have our data, and we're going to do the same analysis with perceived physical appearance. Our predictor variables, though, and our predictor variable will continue to be quad BMI, but we're going to add sex to that because we want to know if males and females differ in how BMI affects perceived physical appearance. So would we call this an interaction or a moderation effect? So by using the term moderation, we'd ask the question, does being male or female moderate the effect of body mass index on perceived physical appearance? So that's what we call it. That's why we are interested in knowing whether or not sex is an effect moderator. Does it moderate the effect? If it moderates the effect, then we'll see that being in different BMI class will have a different effect on perceived physical appearance for males than for females. So let's go ahead and run this. this is now starting to get a little more complicated here. So we're going to go to the general linear model, right? General linear model, and hit univariate. Univariate means that there's only one dependent variable. Okay, so let me reset this. There's only one dependent variable. If it was multivariate, that means we'd be measuring the effects on all dependent variables at the same time, which is very efficacious, but it's not what we're going to do here. So our dependent variable, again, is perceived physical appearance. It goes under dependent variable. Our fixed factors, I'm not going to talk about the difference between fixed and random factors, except for to say that fixed factors mean that the effects are the same across populations. With random factors, you can have different effects across different subpopulations, which we're not really dealing with here. So we'll start with 4-level BMI is one fixed factor, and then we'll add sex as the second fixed factor. Sometimes you might want to control for covariate. There's something called analysis of covariance or ANCOVA, and in that case you remove some of the effect of other variables from the dependent variable. So perhaps we might want to remove the effect of, say, depression and perceived physical appearance. Depression and perceived physical appearance are probably strongly correlated to one another, right? If one doesn't believe he or she is attractive, one might feel more depressed. So we could actually remove some of the variance out of perceived physical appearance by using depression, but we won't do that here. That's just for your edification. Let's look at our model here. Okay, we're going to hit that model link or button and go to customize. Because one thing we want to do is test the interaction. We want main effects. That means that's the effect of each of these by themselves on our outcome variable. Oops, let me go back there. I have to hit main effects, right? And do that. Okay, so we want the main effects, but we also want all two-way interactions, or just the interaction effect. In this case, there's only one, but if we had more predictor variables, we might have lots of two-way interactions. We only have 2 predictor variables, so there's only going to be one. It's only going to be one interaction. I have to highlight these again, apparently, and go here. So our model now includes both the main effects and the interaction effect. We can hit continue. Here, plots. We definitely want to plot the interaction effect, if there is one. So we're going to set up our figure so that, body mass index is on the horizontal axis, and being male versus female is on the vertical axis. Okay. We wouldn't do separate plots. You do separate plots if you have 3 predictors in there. We'll only have 2, and then you have to hit add so that it goes right down here. See, so these are the plots, and you continue. And then that's all we're going to do right now. Let's see if there's anything else we want here, any options. Still want to do a homogeneity of variance test. You could do post hoc test, but in this case, I'm not going to do the post hoc test because I just want you to see what it's like to do this type of analysis, and then also to interpret the interactions if there are any. Okay, so here's our output. Again, here's your code. Remember, for those of you who are interested in coding, if you double click the whatever the box is for that code, and then you highlight it, you can copy this and paste it into your own very own syntax file. Right? Voila, you can run the same analysis from syntax, which again is going to be coming very handy one day if you're dealing with large data sets. But let's go back to our results here and see what we got. Alright, so this gives you some look into what the between subjects factors are. There are, of course, BMI, quad level BMI, and sex, and how many individuals are in each group. You can see that the groups are pretty even because, again, I divided them into quartiles. Levine's test for equality of variance. In this case, now we have a lot of different groups. We don't just have 4 groups. We have 4 times 2 makes 8 different groups, right? There's each of the BMI for males and females. So there's 2 different. There's male versus female. There's 4 in each. 4 levels of BMI. So 4 times 2 is 8. So we do the equality of variance test here, and we passed it, right? Now you know why we passed it, right? So just if you don't know why we passed it, remember, think about this. Okay, so our null hypothesis is that the variances are equal. Our test, Levine's test for equality of variance, is testing whether or not the variances are equal across groups. So the null hypothesis is that the variance for each of the 8 different groups is the same. The alternative hypothesis is that if they're not, and because our p-value is larger than our alpha, whatever it is, say it's 0.05 or it's 0.01, 0.10, it's still larger, we fail to reject the null hypothesis. So we can assume equality of variance. Here's our familiar ANOVA table with some differences now, right? So we have the intercept, we have the quad BMI, the male, the quad BMI by male interaction. What are we looking for here? Well, we're interested essentially in knowing whether this interaction is significant. So if the interaction is significant, we will go ahead and interpret it. If it's not significant, we won't interpret it. And if we look at the p-value associated with this interaction, it is greater than 0.05, it's greater than 0.10, so our interaction effect is not significant. This is telling us that the effect of body mass index on physical appearance does not differ for males and females. Indeed, if we look at this figure here, where we have quad level BMI on the horizontal axis, and then essentially what we have here is we have male and female values as different lines. You can see that they tend to be, males tend to score higher than females across all levels of body mass index on perceived physical appearance. So males don't really care, right? Now you'll notice with females, as one's weight increases, there's a much greater chance that a female won't think she's attractive. But for a male, there is some dip, but then it's kind of starting to level off at the higher levels. So males are, they're full of it, right? We always think we're very attractive. So that's what this story is telling us. But we don't interpret the interaction effect because there isn't none. One of the telltale signs of an interaction is when lines cross each other, and they're not crossing each other, so they are almost parallel, although they're getting a little wider here. In terms of interpreting the remainder of the model, well, we know that there is a main effect for males because we can see the males and females differ on perceived physical appearance, right? Their p-value of the f-test is 0.034, which is less than 0.05. So at an alpha of 0.05, we have a significant finding. Also, there's a main effect for quad BMI, right? So there are differences in body mass index, right, among the different groups. And from what we saw before, it's most likely there were 2 specific groups when we did the Oneway ANOVA, so it's probably similar. If you look at, and it's probably similar there, right? Overall, there certainly seems to be a drop between that. The high point was moderate and the low point was highest BMI. That's what we saw in the Oneway ANOVA, that those 2 were significantly different. That ends this wonderful little lecture for you all, video lecture for you all, and I hope you enjoy. You should go play around with this now. Have some fun. All right, bye-bye.